So this is the HandShake, first iteration of a project that is ongoing. This is the final product of a senior design project here at Oregon State. I'm going to show you just a few of the features of the HandShake. First, you can see the on button. This allows the servo to be turned on and off safely independently of the control system, which you can see this wire here. That's a USB connection to a computer which is receiving serial data from the microcontroller built into the HandShake. Okay, so this is off. I'm pulling up and nothing is happening. Turn the servo on. It takes data from the gyroscope and accommodates the changing position of the hand. Now, because we're simulating only postural tremors in this version of the HandShake, the expectation is the user will hold their hand up when using the device, so that this edge case, which happens here when the thing is not supported, where basically the gyroscope senses motion due to gravity, so the servo will provide motion in that same direction. There's a positive feedback cycle where it ends up just hitting the extreme edge of its motion, which is stopped mechanically on the other side. Tremor frequency and tremor intensity can be adjusted independently. Again, this is dependent on the idea that the user is holding the thing up, so it's just because of the force of gravity, it's at the bottom there. I'm now going to put the device on and show you what it looks like with the user having a tremor simulated. So the process of putting the HandShake on is one of the significant areas that need to be improved. At the moment we're using these ties that are sort of ratcheted down when you're putting it on. It's actually quite difficult for a single person to put it on themselves, which in this next iteration is a major design goal, for one person to be able to put on and use the device. There's another one here. Tension the strap. So I'll talk about in a little while. In its current iteration, the HandShake is quite a bit too long. There's no need for it to be so elongated. Alright, make sure the cable's in good position. Alright, I'm going to turn it on. Okay, so this brings up another major problem with the device. The tightening system needs a lot of work. It only kind of works at the moment. So I'm going to turn this down for a second so you can see. There we go. Turn this down for a minute so you can see this in action with a user's hand. You can see it can accommodate a number of different speeds, although at the moment it is only at a couple of distinct speeds, discrete steps, which is another major change that has to happen. And now the frequency at its lowest setting, you start to get this kind of nice 1 or 2 hertz tremor. Unfortunately, you're seeing another major flaw in the system here with this cable not staying in tension the entire time. There's a lot of friction between the wrist and the cable connection, which is obviously something we need to fix. There we go, that's a nice, fairly low displacement but high frequency tremor. Again, it's not translating as well as one would like, but that's a problem that needs to get solved. Let's write some stuff. So I'm going to write hello world. And I'm going to write the same thing with the intensity at 0. So you can see the top one, you might be able to make out just a little bit of tremoring compared to the bottom one. I try to keep my wrist more or less in the same position. The rest of my arm starts to rotate. That's not a voluntary motion. I'm just trying to keep my fingers in the same position. So keeping my arm straight, trying to keep my hand in the same position, and allowing the rest of my arm to go a little loose. So this is a demonstration of the emergency shutoff button located here on the outside of the arm. It's put there so that if a user is in distress, they can slam it down quickly and stop. It's a hard power stop to the servo here. There's a number of just sort of implementation details that are indicative of the fact that this is very much a prototype. We're thinking that for the final version, we're going to have, rather than 2 knobs which control frequency and displacement independently, we're just going to have 1 knob, and exactly what that does depends on the tremor profile selected in the software side of this project. So that's on the computer. I think that the addition of an accelerometer and possibly a flex sensor just for physical edge cases would not be a bad idea, but so far, with this fairly restricted mechanically version, the gyroscope has proven to be quite effective. It's only this tall because of the board that we selected. It's an off-the-shelf board, so we can dramatically reduce the profile of this, which is important in future iterations because, as you can see, it's almost interfering with things. We need to find a way of better attaching the driving cable to the wrist, because this does not work very well. It's further illustrated here. This is also not very good. You can see quite a bit of friction as it's going through these eyelets, and that's just caused by the fact that this cable is undergoing a lot of stress due to being sort of jerked around. At the moment, you can see that the cable goes from the servo through 1, 2, 3, 4 eyelets, or at least points of connection. I firmly believe that this can be put down to at most 3, and I think as few as 2. So some kind of pulley here, which goes either through another intermediary or directly to the eyelet or pulley or whatever, the point at which it's at its maximum attitude, so that it can get as close to the 90-degree normal from the wrist position that would be sort of ideal for, at least as far as that one thing is concerned. See this flexion here, which may or may not be desirable, but it was not taken into account when we were designing this. This was assumed to be a rigid piece, so if it is desirable, we need to be more aware of that fact. The electronics package over here can be a great deal or smaller. At this point, this was only selected because we were able to find a case that could support the emergency shutoff switch that we could slam down. That's an important design requirement, that it be durable enough to be sort of slammed into a table or something like that, because it is the most, I would say, the most important safety feature on the HandShake. Another important design requirement is designing for people at the extreme ends of the population. And to that end, we have these rigid pieces which attach these two. I'm not especially thrilled with this as a solution. It kind of works, but as you can see, it was done a little hastily. So I think this needs a better solution as far as that's concerned. If we have a pulley here at a convenient angle to get to where it needs to go. We can reduce the length here, thus reducing the amount of friction that's being put on the cable. A good portion of this is about the spring, but if we turn this extension spring into a compression spring and integrate it into that pulley, I think we'll be able to sort of hit two birds with one stone there. Obviously the cabling is pretty prototypey as well. That's something that we need a lot of thought put into. I think that there's a lot to be learned from wrist braces, and I have purchased one of those in an effort to better understand how that works, and I believe that we can end up with something that is much closer to that rather than the sort of tube sock that needs to get ratcheted down. I'm taking the device off now. As you can see, it does not take as long as it does to put it on, but it's not especially comfortable and puts a great deal of wear on the device, which is a problem. And that's pretty much it. That's the HandShake. Thank you for your time.